Hey, hi friends. Good afternoon. Yeah. Hey, good afternoon, friends. Good afternoon. Okay, let's start. I'm just waiting for others to join in. Hey, good afternoon. Yeah, good afternoon. All right, let's start the session, friends. Good afternoon once again, everyone, and let us begin. So we started with the foundational concepts of R programming. Then we understood the packages, which are nothing but collection of multiple functions, data sets, documentations. These are all predefined functions, right? Pre-written functions. So these functions which are user defined, somebody else has written these functions for us, and we are basically utilizing these functions for our purpose, right? These functions are made available to us as part of this as packages. So we are simply downloading them and making certain tweaks to utilize these pre-written functions as inbuilt functions for us. For somebody else, it is user-defined, custom functions, they've written it. And then the core community decided that, yes, these functions are something everybody can utilize. So they've converted that into a package. So these packages will now act like inbuilt functions. All right. So that's about the packages. Then we have started with dealing with the data frames, data sets. So thanks to these inbuilt packages, we also have data available for our practice, right? So data sets are provided to us. Yep, and we're using all these inbuilt data sets on. Question mark of any of the data set name or any of the function will give us a wealth of documentation in our programming. And we're taking the advantage of these available resources for our practice, right? And if you have any additional external data, then you will also be loading that external data into your system, isn't it? So that's what we have learned. Loading the data from text file format, from CSV file format, Excels, then JSON, XML, and various other statistical tool related data sets also can be loaded into our programming. And once we have the data loaded, we will start doing the processing on the data, churn the data. Because ultimately we have to try and analyze the data to make sure we give some value to the businesses, right? Now this data is in digital format and it is of good volume. We cannot do manual calculations anymore. We are living in digital world. So we use this open source programming language, which is very easy and fun to learn and fun to write codes in this, right? For business inferences, to extract information out of this data. So we started pre-processing the data. We looked at missing values. We checked if the data has any missing values. We have to address that. We've also checked whether the data has outliers, extreme values. We have to address those things. We also understood if the data have to be converted from one form to another form, the data types. This is called as typecasting. If I have a very big data, continuous data, then I convert that into bins so that it would be easy for us to analyze. Then the other way around also, if I have categorical data, non-numeric data, then converting that into numeric form using dummy variable concept. This is also something that we have learned. We have understood the statistical calculations, descriptive statistical calculations, mean, median, mode. This calculation will give us the characteristics or the representation of the value, of the data set. Then variance. This talks about spread of the data, right? So when we calculate these descriptive statistics, right, when we do calculations on these data points, we will also come to know that there are certain things that we have to manipulate in the data, like outliers or missing values, right, all these things. We also have to learn whether the data has the appropriate pattern in it, whether it follows certain conditions, properties. So as part of that, we evaluate the distribution of the data. If the data is discrete, then very easy, not an issue. But if the data is continuous, then we have to verify the data whether it follows normal distribution properties or not. And we use QQ plot to verify it. So thereby we are also bringing in the visualization aspects. When you are trying to understand the data that is shared with us, along with these statistical measures, first movement, second movement, third movement, fourth movement, along with these calculations, we also try to look for visualizations. Because when you look at the data from visual perspective, right, if you can see, then it will be easy for us to interpret. Right? Mathematical calculations give you some numbers, but actually visualizing the flow of the data will give you much more in-depth insights. So visualizations. We did bar plot, line chart, dot chart, histogram, box plot, pie diagram. Right? Then QQ plot is also something that we have to see. So all this is preliminary analysis. We call it as EDA. And this EDA is the third step of the project management methodology. For any data science project, we apply certain process, right? We have to go through certain process. That is project management methodology. CRISP DM is what we're talking about. And data pre-processing is the third step. Right? And once we have understood each and every column as part of our univariate analysis, we go to bivariate analysis. Two variables taken together. And here we are trying to understand the relationship. Right? Relationship between these two variables. And when we do that, if you want to understand the relationship, visualizing the data would be the first thing. And this visualization is done using scatter diagram. This is the default visualization technique for two variables, bivariate analysis. And scatter diagram basically is talking about three important aspects. First one is the type of relationship does these two variables have. We plot data on x-axis and the other variable data on y-axis. And we get data points, right? In the x and y plane, scattered data will be obtained. And when we look into the flow of the diagram and flow of that data in the scatter diagram, we will come to know what kind of flow it is. That basically is nothing but what kind of relationship does these variables have. And we are trying to find out if these variables are having consistent relationship or not. That is what we try to evaluate. When I say consistent, it is nothing but linear relationship, isn't it? Linear, straight line. The pattern should be straight. Then we can say, yes, it is consistent relationship. Then we look at, along with this consistency, we are looking at what kind of effect is this? Right? What impact does x-axis put on y-axis data? Right? Now, when we look at this, you will come to know that the x is directly impacting y or inversely impacting y. So we interpret the direction of the scattered data. If it is going upwards, then we say direct proportion. If it is going downwards, it is inverse proportion. Then the third point scatter diagram also speaks about is the strength. How strong is the impact of one variable on the other? We remember always y is equals to f of x is the equation, right? So we are talking about output variable on y-axis. The variable of interest will be plotted on y-axis. And then we have x-axis, which is a factor which is influencing y. Okay, x and y-axis we plotted here. And we are talking about the spread of the data in the visualization. If the spread of the data is very high, scattered data is there, that means the relationship between x and y is weak. X is not able to impact y much. Y is getting impacted, but not because of this x. Probably something else is impacting. Right? So if scatter is less, then we can say that x is strongly impacting y. So these are the three important things that we need to analyze. But when we talk about x impacting y from the strength perspective, strength is always subjective in nature. So what we do? We look for correlation coefficient. Yeah, we look for correlation coefficient. That correlation coefficient is a constant. This is what scatter diagram talks about. This is the disadvantage. Strength is subjective. So we go with correlation coefficient, which is represented using small r. The thumb rule says if your small r is greater than 0.85 from the magnitude perspective, then we say it is having a strong relationship. Right? We say the data has, the features basically have strong correlation. X is impacting y at a strong value. And as I said, different textbooks, different people have different opinion here. So if you say less than 0.85, then it could be moderate or weak strength. Now, how do you define what is weak, what is moderate is up to you. Different books come up with different strategies. We can say anything less than 0.5 or 0.4 is a weak relationship, and between these two, it is moderate. But the range, always remember, small r can take range of values which span from -1 to +1 only. Right? If you talk about magnitude, then it is from 0 to 1. And yesterday I also explained how would the shape of the data look like if there is no correlation? No correlation means we have no impact on y when you are altering x value. That is no correlation. If that is the case, then irrespective of what is the x value, y will have a constant value, right? So you will get a line which is parallel to x-axis. Remember that. Okay, good afternoon. Please confirm, guys, if you are able to hear me or not. Some people are able to hear me. Please confirm. Yeah, that's right, Fani Kumar. I'm able. Yeah, okay, you're able to. Okay, perfect. Thank you, guys. Thank you. Just wanted to confirm. Okay. All right, so this is what we discussed, right? And the correlation coefficient is a parameter that we look to quantify the relationship, because your scatter plot will give you a subjective inferences when you're talking about relationship, right? This is bivariate analysis. Then we also discussed about multivariate analysis, right? Multivariate analysis is a little tricky concept because your computer screen, our human brains are designed to deal with two-dimensional data, right? So I'm taking two variables and plotting on x and y axis, then I'll be able to interpret and I'll be able to see the data. But if I have greater than two variables, if I have 3 variables or 4 variables or 5 variables, then the problem is you cannot visualize all this data on a two-dimensional space. In 2 dimensions, you can take one variable on 1 dimension, right? So to deal with these multiple variables, we do a little alterations, adjustments. Right? What is that adjustment? We basically take data in pairs. We take the data in pairs, right? And then visualize. So when we take pairs, that means you take 2 variables, right? You take one variable on one axis, the other variable on another axis, and plot it. So this is basically multivariate visualization that we do. Of course, we'll have different manipulations, different kind of visualizations that we can try and do, but this is the simplest approach that we take. Yep. So that's about visualization, guys. Multivariate analysis. Now, for predictive analytics, let's say after you do descriptive analytics, you understood what is the challenge that you have to address for the clients, your businesses. Now you probably have to deal with predictions. So if it is a predictive problem, right? If you have to do predictions, then we go with y is equals to f of x equation, right? Y is equals to f of x equation. Now this y is equals to f of x is the base equation, which basically says try and find out the relationship mathematically between x and y. So scatter diagram, when you go with scatter diagram, it clearly explains on what kind of relationship is there between the 2 variables at a high level. In a 2-dimensional space, what is the relationship? So the base equation or the simplest equation is explained as the equation of straight line. In our school days we have learned, right? So we are keeping things simple here to begin with. So if you identify that the 2 variables are having linear relationships, straight line relationship, then we will try to fit in a linear line there. right? So that we can mathematically express this relationship between x and y. And do you remember the concept that we discussed yesterday? How to find out that equation. Now you will have a lot of relationships, I mean different types of relationships in x and y. But what we are trying to do here is to try and fit in an equation which can explain that relationship. But when you're trying to fit in this equation, you have to try and find out the best equation, best fit. So what is that best fit equation, friends? Can you think of the concept that we discussed yesterday? What is that? Yeah. No? OLS, very good. Very good, very good. Yeah, so people are there who are really interested in learning concepts. Wonderful. It feels so nice to me. Yeah. So OLS is ordinary least squares. That's a full form of OLS. This concept is applied to find out the best equation. Because when you look into the real world scenario, the data will be scattered. We can draw any number of lines. Out of these different lines, we need to identify the best line, isn't it? And that line should be giving equal importance to all the data points in this scattered data, right? Among the scatter, each data point is equally important. That means the line has to be as close as possible to your data points. We need y. Given x, we need y. But this mathematical equation, because it cannot touch each and every data point, it is a simple mathematical equation, a straight line equation. So when you substitute this x, you will get a predicted value. We call it as predicted value, right? Or we say fitted value. We're trying to fit. This y hat will be on that straight line that we are drawing. But actually the data could be anywhere here, right? That is your y. That is this y. Right? So we need to try and reduce the deviation between these two. And we call this as error. The deviation is error. So I can say the actual value is equals to predicted value plus error. But the predicted value is the equation of this line, which is expressed as y is equals to beta naught plus beta 1 x, some constants plus error. Less the error, better the equation. OLS is trying to make that error to 0. Magnitude of the error should be 0. Right? So when you take errors and do the summation, it becomes 0 anyways. So to get the magnitude, we do the squared errors and do the interpretation. And we try to find the error line which gives us this squared errors magnitude as the least magnitude. That's the concept of OLS. This is what we've discussed yesterday, till yesterday. And as part of this, we've learned about linear regression. This is the fundamental, or you can say this is the most popular shallow algorithms. We call them as shallow algorithms, or you can say explainable algorithms, based on statistical inferences, statistical calculations. Right? You can explain them. And we go with linear regression technique when the value that you are trying to predict, the output that you're trying to predict is a continuous value. Because your data could be anywhere on this line, we don't know, right? So if it is continuous, then we go with this logic. Of course, there are various other techniques that you will have to apply when your data is non-numeric, or I should say discrete. Yep. Now, today we are going to try and understand how to make sure we get a better equation. Because here you are trying to predict this, fine. But is this actually equation solving this data? If it is, how well it is solved? Now, in order to understand that, we have two metrics that we need to look at. Yesterday we discussed about this R squared, which is coefficient of determination. Right? We call it as coefficient of determination, which is also known as goodness of fit. How well the line is fitting the data. Right? That's what we are trying to understand here. Okay, coefficient of determination. If entire data is falling on that line, then R squared will be 100%. If none of the data is falling there on the line, then R squared will be 0. So R squared basically is capturing the changes that we are able to capture in Y using this equation. Y is equals to mx plus c. I'm writing it in this format. So when I know x, given the value x, how well can we capture the changes that are happening in y with respect to that x, of course, right? So if you are able to capture the variations in y using this x, right, then obviously you can reach to 100% accuracy or 100% variations capturing, or no variance at all captured, no variations in y capture. Hence we say 0 to 1 is the range of R squared. This is one metric. The other metric is the R itself, the error itself. But remember, error we have to square the error and then do the summation. Right? Square error summation has to be done. But that would not be representative. Hence we take average, MSE. But this also, of course, you can interpret this way, or you can also take square root of this error so that we get the units also back. So we are using RMSE calculation as other metric to evaluate the model. Okay, how well we are able to fit the equation to the given data. Why? Because we have to tune the data or tune the model so that we get better fit. Ultimately, we are trying to get better fit. You cannot blindly take a model which is not fitting the data properly, because ultimately using this you have to predict the future cases, right? The unknown cases. So we are trying to fit the model to the data in a better way. Okay, and there are a bunch of other things that we discussed yesterday, like the p-value is something that we have to look for. We check p-value, which is basically known as the significance value. So your p-value will be internally calculated because you are estimating some coefficients here. The chance of going wrong, right, when you are trying to calculate these coefficients, beta naught and beta 1, is measured as P1. And industrial standard for the significance level is 5%. That's 0.05. That means your management is going to allow you till 5% mistake. But if you are going beyond 5%, then it will not be accepted. Simple. You cannot basically use that particular solution. So we validate or we evaluate the equation that we are getting using these p-values. That basically means your beta naught and beta 1, the constants m and c that we were talking about. We need to validate them, whether they can be used or not. Right? When the algorithm is getting trained, it ultimately gives you what is beta naught and what is beta 1. Right? So it is checking whether it is correct or not using the p-value. This is also something that we discussed. So now let us try and fine-tune this equation. Okay, so we will try and see how do we implement a linear regression model using R. Okay, so we will go to R programming and we'll try to implement this entire steps that we discussed in sequential order, one after the other. Okay, let me erase this. Now the first thing that we need to do is to load the data. Okay, I'm doing regression on an inbuilt data set. Let me take cars. We've already worked with this cars, right? It has two fields. Speed and distance. Now, are these two related or not? We'll have to do analyze on the relationship. But before that, as soon as we get the data, we need to first do univariate analysis. EDA. Right? So as part of EDA, you'll calculate first movement, second movement. We'll try to interpret the distribution of the data, visualizations of the data, right? So let's try and do that. Now I would check what is the mean here. Mean of cars, dollar, speed. Mean is so much. Mean of cars, dollar, distance. Right? Then you might want to look at minimum and maximum. So minimum, cars, dollar, speed. I'll just copy this and paste it here for distance. Minimum of our speed is 2, distance is, sorry, minimum speed is 4, distance is 2. Similarly, I'll do max. I'll just copy these two, paste these two. So spread of the data is being interpreted here. So maximum distance is 120 kilometers. Speed is 25 kilometers per hour, probably, right? So that's the range spread of the data. Then you also want to check median here. Let me check median also, just to understand that we do not have outliers. We also will check if we have missing data or not here, right? How do I check? Is dot NA. Is dot NA. So I'll do sum of is dot NA of cars. Okay, we get false, false, false. Everything is false. So I don't have any truths. So that means we do not have any problem. No missing values. Then we are also checking spread of the data. Here we will also verify variance. Just copy this and paste this. Variance or standard deviation. We verify for that. Like this, we need to do descriptive statistics, right? And then we'll also come up with visualization. So I'll say bar plot. As I said, this is the base visualization technique that we will have to go with. So bar plot of speed is that, bar plot of distance is that. Then we'll also come up with histogram. That's the histogram, right? And we can see that histogram of distance is a little different from histogram of speed. It looks more like a bell-shaped curve, but here I see skewed data, right? So visualization is giving us better details. We'll also check box plot. I have an outlier in distance. Right? Clearly shows that it is not symmetrical in nature. These both values are numeric and continuous in nature. So if your data is continuous, then what we do? We have to verify whether this data is normally distributed or not, right? So let's also check for that. How do we check whether the data is normally distributed or not? How do we check that, guys? What we do? Yeah. How do we do, guys? QQ plot, that's correct. We see QQ plot. So I'll say QQ plot. Let me put this. QQ plot. And we'll also come up with QQ line. I'll just put this below this. So I'm checking whether this is, oh, sorry, my bad. It's QQ normal. Yeah. QQ line, yeah, it is normally distributed. And yeah, this is also normally distributed. Even though I have outliers, majority of the data is falling on the straight line, right? So this is normally distributed. Yep. Now we did so many things here, right? So many things. Univariate analysis is what we are trying to do. But can I have a single function which can basically help us interpret all these things? Oh yes, we do. That is summary function. Summary of data set. When you do this summary of data set, it is a single function which gives us a lot of details. And we will be able to interpret all this. When I did summary, you can see it calculates a 5-pointer. Right? 5-pointer output, your box plot. It gives us minimum, it gives us maximum. Minimum and maximum. It also identifies the median, it also identifies the mean. 25th quartile and 75th quartile. Mean is the additional calculation which this summary function does apart from box plot calculations. All these are box plot calculations, right? When you say box plot, it is just going to show you the visualization. When you do summary, it is calculating all those things and showing you. Now, how do I quickly interpret whether there is an outlier in this data or not? Summary is a very widely used, or in fact, everyday command that we use. Okay? So we'll try to draw a box plot here for speed. Minimum is 4. Okay, I'll draw this. This is minimum. Okay. Minimum is 4. I'll draw maximum is 25. Median is 15. Right? Exactly median I have to draw, which is 15. But what is the difference between this and this? (15 minus 4, 11). 15 minus 25, 10. So not much deviation. Right? That's one thing that we can understand. Now, first quartile and third quartile, let us try and plot that. From median, what is the distance of first quartile? 12, right? This is 12. So 12 minus 15, you see, minus 3. 3 units away. At the same time, what is the difference from your median to third quartile? This is 4 units. So not really much of variation, but a little tilted. Okay, here you have 3 units, here you have 4 units, a little tilted. And then we also have to see from 19 to max, what is the distance? This is 19. So how much is this? This is 6 units. From here, what is the minimum distance? So your value is 12. 12 to 4, what is the distance? It is 8 units. Yeah, it is 8 units. Right? So you are basically seeing a visualization which is more like a bell-shaped curve. That's what your box plot also shown you, right? This is what you got. That's exactly what we are trying to draw here. Box plot. You can also put it horizontally. So we will just tilt this to horizontal, equal to true. That's what we did. Similarly, let us now interpret distance. So I'll draw line. You can extend that later. I'll draw median first. This is 36. Median to minimum, how much is that? 34. What about median to max? 36 to 120. Very huge difference. 96. Right? You think 96 is it? Or 86? 120. If you remember that, 86. Let's say 86. Yep. Not 96. How much is this? 96, right? Yeah, my bad. I'm very poor in mathematics. Yeah. So that means this distance should be more. This is 120. This is 2. Next. Distance from 36 to first quarter. How much is this? 10 units. Distance from median to the third quarter. How much is this? 20 units. 36 to 56. So 20 units. So here we will also show greatest. Right? We also have to see what is the distance between these two. It is 8 units. Not 8 units. How much is this? This is 24 units. Whereas this 56, this is 56 to 120. So this is very huge. Right? So this way we interpret the visualizations. So you can immediately look at these numbers and try and understand the spread of the data, visualization of the data. That's exactly what we have drawn, see? Right? So a simple summary on your data set will give all these required details for us to understand whether there are outliers in it, whether there is spread symmetrical or not. Right? What kind of variation we do here. All those calculations can be easily interpreted by this visualization, this calculation. Very simple, check mean and median difference. If it is too huge, that means there is an outlier, very simple. If it is different, a notable difference, that means the visualization will not be symmetrical. Maybe there may not be an outlier. Maybe, we don't know. But we are trying to see whether the variations are too much or not. So this way we interpret the entire data. This is univariate analysis in a single command. Now then we come to bivariate analysis. So here we say bivariate analysis. As part of this, we come up with scatter. So I'll take speed on x-axis, distance on y-axis. This is your scatter diagram. So we have to interpret. You can see that the data is like this, right? If you carefully observe, majority of the data is here. Majority of the data is here, right? So this is positive direction, of course. It is linear, kind of linear. Scatter diagram interpretations. Strength may be weak or may be moderate, we are not sure. So we are going to calculate the correlation value, correlation coefficient of these calculations. Oh. Correlation. What is a correlation? Moderate relationship. Right? We identified that the relationship is moderate. Close to being strong, but still it is moderate. Anything less than 0.85 is moderate. Right. Wonderful. Next. Now, once we have analyzed this, we need to come up with regression analysis, linear regression. I'm calling that linear regression as model 1. And we say y tilde x. So let me take the distance as output. If you go at a certain speed, what is the distance that you will be able to cover? So we need to say y tilde x, regress output using this input. Done. Very easy, right? We have seen this already. Then we do summary of M1. When you do summary of M1, it gives us these calculations. Of course, we look at residuals. But remember, it is giving us a summary of the residuals. So it calculates minimum, maximum, first quartile, third quartile, and median. Why is it not showing mean here? When you did summary on the original data set, it was giving us 6 points. Minimum, maximum, first quartile, third quartile, median and the mean. Whereas when you did summary of the model here, it is showing only 5 calculations for your residuals. Why? We can do various other visualization techniques also, Shishidhara. ggplot is also one of the visualization package using which you can come up with the scatter diagram. Yes. No. No, that's not the reason, Srinivasa Rao, why it is not showing the mean calculation in the summary. Yeah, anyone else? For skewed data median, no. Oh, do you mean by for symmetrical data you do not have median? It's a mathematical calculation, right? You can do calculation on symmetrical data also. Okay, what are the properties of errors here? Residuals. For regression, what is the logic that we discussed? What should be the errors? Properties? We discussed about best fit line, right? OLS. What does it give us? What is that minimum? So the OLS is trying to find out the best fit line, right? And when you say best fit line, the sum of the errors will be equal to 0. Sum of the errors is equals to 0, isn't it? That's what we discussed. If sum of your errors is 0, what will be the average of errors? If sum of errors will be equal to 0, because you're trying to find out a line which is passing through the data in such a way that it is as close as possible to all the data points, right? So if I say sum of these deviations that we are getting here, if those sum of errors is equals to 0, then what will be the average of errors? That will also be 0, right? So if mean is 0, why you have to represent that? Not required, right? Because for every linear regression model, this is a property that your errors have to follow. Your line has to follow these properties, right? So there's no point showing you the mean of the residuals. So if you want to cross-check this, we can also do the cross-check here, right? Let's do that. So your M1 here is capturing a lot of values, 12 different values are there. I'll put M1 dollar residuals. When I do that, these are the errors for all the 50 observations that your model is giving. Right? These are errors. Now you can check what will be the sum of these errors. What is that value? 4.32987 into e power 10 minus 15. So what is that? 0, right? You can also check average. Average will also be obviously 0. Yeah. So there is no point in representing that mean zero error here. Okay. That's one thing that we need to observe. Then coefficients. These are nothing but your M and C. This is M, this is your C. So we represent that as beta naught and beta 1. What is your equation? Y is equal to beta naught plus beta 1 x. This is how we represent. This is intercept. So that intercept is here. This is M. That is this. So your equation, what is y in our case? Y is the distance. Distance is equal to minus 3.9324 into speed. This is your equation. But can I use these values? Can I use these constants that we got? Right? So in order to interpret that, we look at the p values corresponding to beta values. And we got values which are less than 0.05. Both of them are less than 0.05. So we proceed considering them in our equation. They are good. They are statistically significant to be used. Right? So we validate the equation like this. But we also have to see R squared, goodness of it. How much is the R squared? It is 65% approximately. 65.11. Right? It's basically 65.11. Yep. Is this good enough? It is like goodness of predictions, predictability. Given the speed of the vehicle, speed of the car is going to travel at a certain distance, and we are able to predict that with 65% accuracy. That's how we can interpret this R square. Yeah, 65% accuracy. But this is only for accuracy, but we also need to look at the error that we are getting, right? So this is predictability. This basically is talking about if you change 1% in speed, if your speed is getting varied by 1%, then your y gets changed by some percentage. If I take that as 100%, then from this change, because of this 1% change in speed, we are able to capture 65.11% of variation from y. Y is getting altered, right? But out of that alteration, 65.11% is caused by speed. That's what this equation is able to explain. Right? So that's what we look at. So only look at this case. So there are various other parameters like F statistic, adjusted R squared, then residual, standard error, then we see standard error, estimate, T value. All these are various things that probably when you deep dive into the subject, you'll come to know. At this point of time, it's not required. Try and understand the logic. That's good enough to start with your learning in regression. Right? So don't look at other things, guys. Not required at this point of time. Only focus on this. Yeah, you can ignore all these things for now. You only look at p-value, this value, then you look at this value. Okay, and of course residues. All right, now I want to improve the predictability. I want to capture more variations that are happening in Y using this X. Right? I want to predict it better. That means your R squared should be increased. But in order to increase that, you need to first strengthen this relationship. Right? That means your R value should be strengthened. The scatter is too high. You need to reduce that scatter, right? So that is basically your correlation has to be increased. Scatter has to be reduced. Right? And there will be another metric, which is error calibration. Remember, your equation would be good. It's called as good when it is giving us least error. Right? So in order to measure that, we need to measure squared errors average. Right? So if I take average of errors, it's giving us 0 as the error, right? 0 as the representative value. That means it's a good fit. Yeah, but what is the magnitude? In order to get the magnitude, we'll say RMSE 1. For model 1, I'm calibrating. We'll say take squared errors first. For square, I'll put power 2. This is taking errors and then squaring them. On the squared errors, you might want to take mean. But this will give us huge value because your errors are high and the units are also high, squared. Isn't it? We are trying to predict distance. So your error is getting in distance. When you square it, you get distance is square. Doesn't make any sense, right? So we take square. This is called as RMSE. Oh, my bad. Square root. So your RMSE is 15.06. Yeah, this is 15.06. Yeah. So, how do I improve this equation is the question. All right. Fine. So we will try to digest these. We have now constructed a linear regression equation, guys. That means we are developing a prediction model. What is that equation? Y is equals to f of x, right? This is the base equation that we started discussing. We are giving a value to this equation, which basically is representing the relation between x and y. That is, your distance is equal to minus 17.5791 plus 3.9324 into your x. X is what? Speed. Right? So this is basically your equation. Now when a new vehicle, new car's speed is obtained, we'll simply substitute that new car speed here and we'll be able to get how much distance it will travel. Right? So that is about your machine learning equation. But is this the best equation? That is what we are trying to understand now. No, this may not be the best equation. So we have to try and manipulate, adjust this equation, tune this equation so that it gives us even better results. In order to interpret the results, we are looking at small r, we're looking at R squared, we're looking at RMSE of each and every model. We will have to record these things. Okay, we'll record these things and then we will compare multiple models. This is M1 that we did. So we'll now do M2. We'll also try and do M3, M4, M5, right? So what is that logic? Well, I'll explain. Okay, I'll explain that logic. And we'll also try and understand how do we evaluate the final model. Okay. So let's see if I have any questions in between now. Overfitting we'll discuss. I'll explain that, Shashidhar. All right. So we'll take a short break now. We will come back and discuss about all these things. Okay. So we'll also try to record these calculations that we have done, okay? Which is nothing but small r. This is correlation value, which talks about the relationship between x and y. Okay, what is x? What is y? X is speed, the car's speed. Y is distance that we are interested in capturing. 0.80, this was the correlation effect. What is r squared? It was 65%. What is RMSE? It is 15.06. This is the details for your model 1. Right? In model 2, what we will do? We'll try and do that in logic now. Okay. So we'll take a short break. It's 3:08. We'll connect in 10 minutes. Okay. 3:18. This is the break, friends. Yeah. Come back by 3:18. We'll discuss about how to tune a regression equation. Hey, hi guys. Hope everyone is back. All yeah. So we are now trying to understand how do we tune the algorithm that we have developed. Algorithm is basically giving a result, right? A model. So how do we basically tune this so that we get better accuracies? Okay, so let me record this. I will basically open an Excel sheet. Okay, let me just create an empty Excel sheet. Okay. Okay. So let me record the output that we are trying to predict. What is the output? Output is the distance. What is the input using which we are trying to predict this? It is speed of the vehicle. Right, the data set is cars data set, so we have input output. What is the correlation between them? The correlation between them was calculated as, let's do it once again, doing this. The correlation is 0.806. 0.806. Right, correlation coefficient. Then we also have R squared. R squared, how much did we get R squared as? When you did summary, we get R squared as 0.6511. 0.6511. And we also calculated root mean square error. RMSE stands for root mean square error, which is 15.0689. So we will mark this. Right. So these are the details that we have captured. I'm just beautifying them. All right. Next. This model that we have developed, right? The model that we have developed is known as a simple linear regression. This is your vanilla model, base model. We call it as base model. All right. Now, we have to improvise this particular result. Right? We have to improvise the model that we have obtained. How do we do that, guys? What do you suggest? This is our scatter diagram. How can we achieve better accuracies? What do you think? The screen is not clear. Only for you, I guess. Others, please comment. Is the screen clear? Okay, I'll zoom in. That's okay. I hope you're not attending from mobile. If it is from mobile, you'll not be able to understand anything. Yeah, coming back to the question, friends. How do we improvise the result? Yeah. When can I get a better fit? When my spread of the data is reduced. Here you see there is a huge spread. If I can try and get the spread of the data reduced, then I can try and fit a line which is passing through the data in such a way that it is close to majority of the data points. You can clearly see here, right? This is the spread of the data between orange lines, whereas between the pink lines, the spread is so high. So this is the error that we will get with respect to the black line that you are trying to predict if your data is spreading wide. But if you are doing spread, I mean, if you're trying to reduce the spread in the data, then obviously the error will be reduced. But how can I achieve this? How can I achieve reduction in the spread? What should I do? Very good. That's right, Lakshmi Kumar. We need to alter the distribution of the data here. The distribution, that is nothing but the spread of the data, has to be altered. In order to adjust the spread of the data, we need to adjust the magnitude either here or both. We adjust the magnitude. We keep one side with one magnitude, the other side will try to adjust the magnitude so that the spread of the data is reduced. This is called as what? Transformations. We learned this transformation technique in deciding, in dealing with normal distribution data, right? We already did this. Normal QQ plot. If you remember, normal QQ plot verifies whether the data is following normal distribution or not. QQ norm. And in order to get that data follow normal distributions, we altered the magnitude of the data. Right? So that's exactly what we are doing here. Transformations. Yeah. So let us try and do the transformations and understand how your model can be adjusted. I'm trying out with transformations. So in order to understand whether the transformation is working or not, we will do plot. Plot of, what did we do? Cars dollar speed, comma, cars dollar distance. This is the original data in its original form. So now what I do is, transformation 1. I will try to alter the x-axis magnitude by, let's say, applying a log. That's it. You just take log of x value and then verify the relation with y. If you observe here on the, okay, let me just maximize this a little. If you observe the spread of the data here on right side of the screen in the visualization section, the plot section. This is cars on x-axis. You can clearly see. This is your cars and this is distance. Now when I applied the transformation, it became log of cars, the magnitude altered. Right? You can observe that magnitude on x-axis is changing. The objective is to make sure that the data scatter becomes less. But this transformation is not actually helping us in a good deal. You might also want to check by quantifying the relationship. So here we will do correlation. What is the correlation here? 0.806. If I apply this correlation on this particular data, it has reduced the correlation. It has not increased, but it reduced. So not a good correlation. Can I apply exponential here? I have applied log, but let's see if I apply exponential, what happens? Ah, pathetic, right? This is very, very bad. So let's see, applying, let's say, square root. On x-axis, I'm applying square root. So it is similar to original data. Let's compare. So original data has 0.8. What about this? Not a good one. How about taking square? So square can be put as multiplied by the same value, or you can put cap symbol and 2. Okay, it's giving us a better, probably a better scenario. Okay. Look at this. Original data is 0.80. It is increased a little better, 0.816. Now, all these experiments that I'm doing are only on x-axis values, not on y-axis values, right? So let us try and see what happens if I do with this transformation. Okay, so I have applied x square. So we'll record this. Distance is taken as is. Speed is taken as power 2. The correlation has improved a little better, 1%. Right? And let us now develop a model. All you're doing is just changing your y will be as is. You're just changing your input by doing square. That's it. You develop the model. M2. Now let's do summary of M2. Did it improve the model anyway? Why it is not working? It should work. Okay, let me just check. Okay, let me. It's not taking. So if you can see, there's literally no change. In the model, there is no change, even though we have squared data taken. Yeah? So there is no point. You get the same results, 0.6511. Your equation beta naught and beta 1 are also same. Nothing changed. Yeah? So your error will also remain constant, but let me try. I'll just calculate this. All I have to do is change this to M2. And this also I'll have to change to M2. RMSE2. Same result. Your equation did not change, right? So you'll get the same result. Nothing will change. When I put here, of course, it is getting adjusted. So this is square transformation. We applied square to your x-axis. Now let's try and do manipulation on y. All these are the transformations which we did on x, right? Now let us try manipulations on y-axis. So again, I'll go back to the original data. Okay, this is your original data and correlation. Now let's take alteration of data on y. I'll do the same approach so that there is no confusion. I'll take log of y. Okay, looks a little better to me, but let's check correlation. See, correlation is increased. It's 0.822 now. We'll try with this, but let us see various other experimentations as well. Square root. Not really, right? It's not giving us good results. Oh, 84. This is actually better. What if I take reciprocal? Let me try with reciprocal also. We did not try that, right? That's it. 1 by this. Not good. Not good. Not good. So I'll not take this. Yeah, will not work with this particular data. So I think we should go with square root transformation, because that is log transformation or square root. Which one is better? Yeah, this one was better, right? So we'll go with this. So again, what I do, I'll take M3. I'll say lm of, what is your y here now? Square root of cars dollar distance. This is your output. Tilde cars dollar speed. You're taking x as is, but y is getting altered. Now I'll say summary of M3. What did I get? My R squared improved. My equation is getting altered. So let us try and record all this. So this is small r. Here I am taking square root of distance, right? Square root of distance. And I'm taking speed as is. And my R squared has definitely improved. And this is my R squared. So let us also calculate what is RMSE here. So I'll do RMSE 3. And then what I'm doing, I'm taking square root of average of squared residuals. So M3 dollar residual square. And RMSE 3 will basically give us 1.01. Does this mean your error is changed or reduced from 15 to 0.1? Such a huge reduction? Do you think that is correct? No, this is not true. Why? Because what is your equation that we obtained here? The equation that we are getting here is square root of y is equal to, remember we are doing square root of y is equal to beta naught plus beta 1x, not y. You get square root of y. So how do I get y? After substituting all the values, once you calculate this, if you do square of this, then this and this gets cancelled and you'll get 1. So you have to do reverse transformation, right? So if you look into the predicted results, or if you look into the residuals to start with, what is your residuals? You say M3 dollar. These are your residuals. Look at them. All these residuals that you're getting are very, very small values because you're taking square root. $M3 fitted values. These are your predicted values. Fitted values are nothing but predicted values for the given input data. So very small data, right? This is not the right data that we need to look at. So what we need to do here is, we need to first do the prediction of the values, get this prediction, right, into a regular form. Right? How do I get this? By taking the predicted results and squaring them. So you can say distance, or let's say your square root of distance, M3 predict M3 using your data. You just say M3 predict. Yeah? When you do that, you get square root underscore distance. That's what we did, right? This is exactly what we did. Now here we need to get what? Distances, not square root distances, right? So we will apply predicted distance is equal to square root of distance whole square. When you do this, this is actually your original, this is your original predicted values that you are interested in. This gives you the actual predictions of your distance. Now we need to calculate error. Residuals is equal to, residual is equals to actual value minus predicted value, right? Error is nothing but original value and predicted value. But what is my original value? Original value is already there with us. In the cars data set, this is your original data. And we are doing subtraction of this data with predicted values. Now you got the actual residuals that we need to consider to measure RMSE. These are the errors that we need to consider. So what we are doing here? You're taking RMSE3. I'm overriding the calculation there. I'm taking square root of mean of residual square. You square those errors, then calculate the error, and finally calculate the square. RMSE3, this one will become your valid value. So your RMSE is 14.76. Right? Now here, what did we do? The transformation we did is square root. But how did we obtain the original result? By doing squared transformation. So here also you called it a square transformation. Here also the model is called a squared model. But the transformation is done on square root on y. So the model is called as squared model. Right? So that's basically what is giving us the best result among the 3 results that we tried out. So this is giving us the best result among all the 3. Right? Yeah. Any questions in this? Now, before I ask questions, it purely depends on the time frame you have, guys. Okay, how much time do you have to do these manipulations? That will basically tell us, or that will basically decide on how accurate your model can be fine-tuned. If you do not have much time, obviously you cannot do a lot of transformations, isn't it? But if you have a lot of time to work with, your client says, okay, take as much time as you can, but make sure you give the best results. So you're going to do a lot of trial and errors, right? A lot of iterations on top of this data in order to bring out the best equation. Okay. Now, before I conclude this as the best model, if I go back to the crisp DM here, so what we've learned here is, we understood these steps: objectives, constants, and project charting. Then data collection, primary source, secondary source, and different data types. Then we started learning about pre-processing the data. Missing values, that is imputation, outlier treatment, typecasting, dummy variables, right, whatnot. All those things we understood, and statistical calculations as well. First, second, third, fourth, plots. All these are your EDA. Right? We learned about these concepts. Now, post doing this, this is all your descriptive analytics, right? Till here it is descriptive. Of course, this is a different task. This is also a different task, but we are doing descriptive analytics. Then I've included predictions also here. Okay. Predictions. That's y is equals to f of x. That's what we did, right? Regression analysis. But don't you think you need to evaluate the model? Because after all, we are using this equation to predict an unknown value when you give x. So I have 50 records in my data set, past history. We're taking past 50 records here. Right? I have cars data set, 50 records are there. Given this data, right, we were trying to identify the pattern using that equation. But what I'll do is, I will take that equation, mathematical equation, and I will try to use this for 51st vehicle or 52nd vehicle or 100th vehicle. I don't have the data upfront. I'm trying to predict it. Yeah, I'm trying to predict this equation. Yeah, predict the value using this equation. But can you consume this prediction is the question. Right? So in order to accept this, right, in model evaluation techniques, what we do is we measure the accuracies and try and apply the comparison models. But you say that, okay, we did this and this is the accuracy comparison that we are doing, fine. This is the better one. But what is the guarantee that this equation that we obtain will work for new data, 51st data? We do not have any guarantee. Why? Because the logic that we have done here is, let's say I have 50 questions. Okay. I am training you on these 50 questions with answers. I'm explaining you the answers. I have questions and answers. So I'm training you on these 50 questions. And when I want to try and evaluate whether you've learned these questions properly or not, what I'm doing, I'm conducting a quiz, but I'm conducting the quiz on the same 50 questions. Now you're already exposed to the answers, right? So the accuracy or the results will be better always. Results will be good. Isn't it? If I'm training you on 50 questions and let's say I'm conducting an exam on the same 50 questions, you will obviously give me good results. Isn't it? But what is the guarantee that the student who has got good marks on this quiz is going to answer the questions pertaining to the same subject, but you don't know the answers of it? So let's say I'm bringing a new question, 51st question. What is the guarantee that those who have secured 100%, for example, on these 50 questions will give answer to this? Do we have a guarantee? We do not have that guarantee because you might have by hearted the question answer pair, maybe. Yeah, you might have by hearted the question and answer pair. So as soon as you've seen this question, you remember the answer, so you are going to print that answer there on the answer sheet, isn't it? But if I ask a new question, you'll put a blank face because you by hearted, you did not understand the subject. You'll not be able to answer it, right? So this is the reason why what we do here is we split this 50 questions into two parts. So probably I'll hide 5 questions and I'll take 45 questions for training. Okay, questions and answers will be there, and I will train you on these 45 questions. Of course, I will conduct quiz here. This will actually tell me whether you are learning or not. Students who are not performing on these 45 questions, I can clearly understand that they are not interested, right? So I can remove them from the training, isn't it? But for the people who are getting good scores, for them, I have to validate whether they're actually learning the subject or by hearting the question answer. So I will choose the best students, the students who have secured very good marks on this. And what I do is I take these 5 questions and test them again. Now for these students, the 5 questions are like new questions, because they don't know these 5 questions, right? They were only trained on 45 questions. So these are like new questions now. So we will check the results on these 5 questions. And what we do? We compare the results with these results. Now if both are similar, then I can get the confidence saying that the student has actually learned the subject, right? But if the results show that on the training data, that is on the 45 questions, if the results are good, but on the test data, the results are very, very bad, then this condition is called as overfitting. So what we were trying to do is, we were trying to tune the model and try to fit it. So we keep on tuning the data, we keep on adjusting the data, we keep on adjusting data so that the data fits that particular pattern well. But when a new data comes in, it might not fit there. It might not be perfectly fitting there, isn't it? So we should not overdo anything. That is called as overfitting case. Right? Now we also have something called as underfit. Underfit means on training data itself, the results are bad. Okay, forget about test data. We don't even verify test data if this is bad. This is called as underfitting model. These are called as underfitting models. For example, when you are trying to apply for any entrance exams, so for example, civils, there will be preliminary exams, right? Preliminary rounds. If you do not qualify in the preliminary rounds, you don't even get a chance to write the original exam, right? The final exam. So that is underfitting. You did not prepare enough to write the exam. You did not even qualify that. So these are the conditions that we need to cross-check. Overfit, underfitting. What we need is the right fit. So overfitting is a case where you get good training results, but test data is bad. Underfitting is train itself is bad. And these are train is good, training data results are good, test data set also results are good. Right? So this is basically your right fit. Overfitting, underfitting, and right fitting, and this is what we need. And these should be similar. Okay, these should be similar. Okay. So this is basically how we fit your, or we evaluate the models. Clear, friends? Any questions in this? Okay, no questions, is it? Yeah, hope Shashidhara, you got the answers for your questions. I'm going in reverse order, so yeah. People who asked for attendance link, there you go. FB link, you can get that directly from the website also, guys. You don't have to rely on us. Anita, you can just go to the website, scroll down. There you go. All the links are available. Yeah, you might want to click on this link. So just go to 360DigiTMG website where you got the book also, right? You might have downloaded the book from here, learning resources. So go there and get your book. Underfit in terms of bias and variance. Okay, what does variance means, Anand? Variance means lot of variables. Okay, when you're trying to adjust or fine-tune your model, you might try and incorporate, you might want to add more and more features. So existing data, you might do a polynomial model. You'll take x and x square, or x cube, or x power 4. So ultimately what you're trying to do is manipulate the model by adding more and more data, right? So that is basically overfitting. More variables means more variance. So that's how you can remember. Variance means overfitting. Now bias is underfitting, because you're saying, hey, if you add more data, more variables, your model might improve. But you're saying, no, I'm fixed with these models only, these variables only. I don't want to add. So that is called as bias. You're biasing your model, saying that you will choose only these features. You don't want to add any additional features. So that's called as bias, which is representing underfit. Hope you can map it now. Anand, that was for your question. Yeah, Saujanya also messaged there. Underfit is bias, overfit is variance. Okay, yeah. All right. Any questions? Any further questions, friends? See somebody asking a question. Okay, so if no questions, then thank you so much, guys. And tomorrow we are going to connect again. Tomorrow we will see how to deal with textual data manipulation. Okay, we'll talk about textual data manipulation tomorrow using R, of course. All right. Thank you so much, guys. Enjoy the rest of the day. Thank you. There you go. Last time, one last time, the attendance link for people who missed the attendance link. There you go. And thank you, guys.